How we doing, guys? We're looking at fundamental applied maths here, chapter 9D, pages 172, 173. This is hydrostatics. We're looking at questions 4, 6, 10, and 12. So to start with, question 4 says a block of wood of mass 20 kilograms floats in water with 3/4 of its mass under the surface. Probably should say a uniform block, so that means 3/4 of its volume as well. It is then put into oil of relative density 0.8 and a piece of glass is placed on top of it. It floats in such a way that the wood is totally submerged, like in this diagram here, but the glass remains just above the surface. Find the mass of the glass. Okay, so to start with, we've got 0.75 or 3/4 of our wood underneath the surface. If it's floating, then its weight is equal to its buoyancy. Now I know the weight is 20 times 9.8, but we're going to go with this as its weight initially. That is its density times its volume times, so mg. And that has to equal the weight of displaced water. Okay, so that's going to be density of water is 1000. The volume of displaced water is 3/4 or 0.75 of the total volume. So 0.75 V times acceleration due to gravity. Okay, and that gives us V's cancel and G's cancel. And if you divide through by 1000, you get rho over 1000. We've seen this type of calculation before, 0.75, but rho over 1000 is the density as it compares to the density of water. That is its relative density. So its relative density is 0.75. Then it's put into oil with a relative density of 0.8. So we've got our block of 0.75. We've got oil of relative density 0.8. And this piece of glass is put on top. Okay, so the weight, as we know, if it's 20 kgs, then the weight is 20 g. The buoyant force acting upwards here, okay, once it's been fully submerged, we can use this equation here from theorem 9.3 that we met in the last section. And the buoyant force that it experiences is going to be the density of the oil around it divided by the density of the object, 0.75. So that means it's experiencing a bigger buoyant force than its own weight, which is 20g. So let me just put 20g in there. Okay, so it's experiencing a buoyant force upwards of 0.8 divided by 0.75 is 16 over 15 times 20, 21.3 g, or 21 1/3 g. Okay, so if it's experiencing an upward force of 21.1.3 recurring 21 1/3 g, the weight downwards is 20 g from the block. Well, the weight from the glass must bring us up to having the same force up and down. So that means the weight from the glass is going to be the extra 1 1/3 g newtons. And I think they ask us to find the mass of the glass, which is 1 1/3 kilograms. Okay, so there's question 4. Question 6 says, assuming the relative density of ice is 0.9 and that of seawater is 1.03, find the percentage of the volume of a block of ice. Find what percentage of the volume of a block of ice floats under seawater. Correct to the nearest percent. Okay, so question 4. Here's our block of ice. Okay, it's floating in seawater of relative density 0.3. It has a relative density 0.9. Water expands as it freezes, so it gets less dense, which is why ice floats. It's less dense than water. If it's floating, then the buoyancy, the upward force, has to equal the weight, the downward force. Okay, well, buoyancy is this volume here, the submerged volume, is going to be x times the total volume. Okay, so that volume is x times the total volume. The buoyancy is the weight of displaced water. So that's the volume times the density of the water, which is 1030, okay, or 1.03 multiplied by 1,000 kilograms per second, kilograms per meter cubed, times g. Okay, so that's our usual weight is volume times density times acceleration due to gravity. The weight of the actual block, so that's the weight of displaced water. The weight of the actual block is going to be, well, its volume. The density here is 900 kilograms per meter cubed. And g is still g. Okay, so g's cancel and v's cancel, and we're left with x equals 900 over 1030. Okay, and that's going to come out as 0.87, or 87% of the ice will be underwater. 13% of it will be over the water. Question 10 says, now there's a mistake in the book here. Question 10 and 11 are all part of the same question. And then at the back, what we have is 12, they have is 11. This is labeled 12, this is labeled 13, 14. A solid piece of steel weighs 40 newtons in air and 35 newtons in water. Find the relative density of the steel. Okay, so let's do that first. We know that it weighs 40 newtons in air and 35 newtons in water, which means it's getting a 5 Newton buoyant force. Okay, so that, according to this equation here, that 5 newtons is the weight of the steel, which is 40 newtons, divided by its relative density. And solving that, we're going to get the relative density is 40 over 5, or 8. Okay, which means it has a density of 8,000 kilograms per meter cubed. The next part of the question says, an open rectangular tank is constructed from 5 sheets of steel, 1 sheet for the base, 2 sheets for the front and back. Okay, I've got the measurements here. It's 80 by 60 by 40 with an open top. Okay, so here's our tank. And it says the thickness of each sheet is 0.15. So 0.15 centimeters is how thick each sheet is. It says calculate the total area of the sheet metal used. So that's going to be 80 by 60 plus 2 times 40 by 60, because you got this and this, plus 2 times 80 by 40. And that is going to give you, so I have this from earlier, that is going to give you 1,600 centimeters squared. Okay, is the total area. If you want, you could change that. That's 1.6 meters squared if you know that there's 10,000 meters squared in centimeters squared in a meter squared. I'm going to keep working with centimeters because they've given us in this question the density of the lake water using centimeters cubed. So I'm going to work with centimeters cubed for this problem. They say find the total area and hence find the mass of the tank. Okay, well that's the area. The volume of the tank, the volume of metal is 16,000 centimeters squared. Each one is 0.15 centimeters thick, so that gives us a total volume of 1600 times 0.15, 2,400 centimeters cubed, and we're told that it is a relative density of 8. Now we need to be a bit careful here. The density of steel is 8 grams per centimeter cubed. We're told that. Yeah. Okay, so yeah, with the density of water is 1 gram per centimeter cubed, the density of steel is 8 grams per centimeter cubed. So we can say that the mass is 2400 centimeters cubed times 8 grams per centimeter cubed. And that's going to give us the mass of this thing is 19200 grams, or 19.2 kilograms. But I'm going to stick with that 19200 grams as its mass. If the tank is allowed to float in a lake, find the depth of the base below the surface of the water. Take the density of the lake water to be 1 gram per centimeter cubed and assume the external and internal dimensions of the tank to be the same as here. So we're going to put this in a lake. Okay. And it's going to float at some height h. Okay, above the water. Something like that. Well, we've got its mass, its weight acting downwards. When this happens, will have to be the same as the buoyancy acting upwards. Okay, well, the weight acting downwards is 19200 g. Okay, mass times acceleration due to gravity. And that equals the buoyancy acting upwards is the volume of displaced water. Well, our volume of water here is 80 by 60 by h, whatever depth it sinks to. That's the displaced water. The buoyancy is the weight of the displaced water. So it's the volume times the density times g. Okay, so g's cancel straight away, and that, by the way, to do that correctly, g would have had to be in units of centimeters per second squared, rather than the usual meters per second squared. But either way, cancels there. We want to get h, so that is going to be 19200 divided by 80 by 60 by 1000 equals h. And our height is going to come out as 19200 divided by 80 divided by 60 and divided by 1000. So we're getting 0.04 meters, which is 4 centimeters. Now, it's question 10. Question 12 says a tank contains water. Oil of relative density 0.9 is poured into the tank until it reaches a depth of 5 centimeters. Show that the pressure at a depth of 9.5 centimeters is twice the pressure of a depth of 5 centimeters. Okay, so here's our tank. The pressure at 5 centimeters is rho GH. So our density, our relative density is 0.9, which means our density is 900 G times 0.05. The pressure at 4.5 centimeters is going to be the pressure due to the oil, which is 900 G times 0.05, plus the pressure due to the water, which is going to be 1000 is the density, G times the height is 0.045, okay, 4.5 centimeters. So this comes out as 900 times 0.05 is 45 G, and this comes out as 1000 times 0.045. That's 45 G and that's 45 G, so this comes out as 90 G. Okay, so the pressure is twice as high. The next part of the question says, at what depth will the pressure be 5 times the pressure at a depth of 3 centimeters? So at a depth of 3 centimeters, our pressure will be rho, which is 900 G times 0.03. Okay, that's at a depth of 3 centimeters. So at some other point, it's going to be 5 times that. So multiply that by 5 and you get the same pressure as down here. Okay, so that's going to be 900 G times 0.05, you've got the original 5 centimeter layer of oil on the top, plus whatever that depth of water is. That's going to be 1000 G times whatever that depth of water is. So G's cancel, and what we will get ourselves, this is a bit of calculator work, 900 times 0.03 times 5 is 135 equals 900 times 0.05, 45 plus 1000 H. Well, moving that over, we get 90 equals 1000 H, and H equals 0.09 meters, okay, which is 9 centimeters. That's that height. The question was at what depth from the top, so you have to add on that original 5 centimeters, so your answer is 14 centimeters from the top. Now, those are the ordinary level questions, I suppose. We've got the higher level question ones to do, which I'll do in a separate video. But before I do, I'd encourage you to go back, pick 4 questions from exercise 9D, questions 1 to 13, and give them a go. Okay, good luck.